Hi everyone, this is the video for the lab number 10. Confidence interval. A hypothesis test has two outcomes: fail to reject or reject a null hypothesis. Based on the sample data, they collect the values of the parameter where the decision is failed to reject are contained in size of the confidence interval. The values that are outside of the confidence interval are rejected. All right. Uh, I didn't talk about the confidence intervals in the video so far. So here, usually we won't do it, right? So only if necessary. But here in the lab, we have to do it. So essentially, I will be explaining here what a confidence interval is, yeah, and how to create one and how to interpret. So uh, the size of a confidence interval depends on three factors: sample size increases, the width of the confidence interval decreases, standard deviation increases, the width of the confidence interval increases, level of confidence increases, the width of the confidence interval increases. Using confidence interval for the population mean, for population means. Every time a confidence interval is calculated, it changes due to the sample statistic. We are attempting to capture the population mean inside of the range. Sometimes the value is inside of the range, sometimes it is not. In the long run, the confidence interval captures the true mean 100 times 1 minus alpha percent of the times. For example, the 95% confidence region will capture the true value of the population mean only 95% of the time. So essentially, a confidence interval is we're going to be given two values, the lower value and the upper value, and we are in hope that the true value for the population parameter is going to be included there. How are we going to be doing this activity? Well, this lab, use the confidence interval applet to complete the lab. If you click here in your activity, you're going to have this page, this web page to the left, this one. WebLink is also available as a course tool in the module. I think this is not true. So where is this? Now, how does this thing work? All right, the true population mean is drawn using a vertical line colored in green. The value of the population mean is supposed to be this one. You see, it's supposed to be represented that where this vertical line is passing through. The confidence intervals that captured or hit here is called hit. Noted by now is 0. The true population mean are drawn in black. The confidence interval that missed the true population mean are drawn in red. And the apple simulates independent experiments, keeping track of the number of confidence intervals that capture hit the true population mean. The relative frequency of a hit is recorded at the bottom of the right panel. So we're going to be seeing that here. The applet will generate a sample from a Gaussian distribution with default value of 9 equal to 20, but this can be modified and report the confidence interval, upper and lower bounds for the population mean. The bounds are calculated from the data. On the left panel, you can choose the confidence level. The default is 95% by moving the slider. On the right panel, you can generate experimental data with n equal to 20 by clicking on the green button sample. The confidence interval along with the sample are graphed. The left panel keeps track of the number of experiments that reported confidence interval that capture the true mean. For example, in the long run, 95% confidence interval should capture the true mean 95% of the time and miss it 5% of the time. All right, so this applet calculates the confidence interval by generating random data. Here, we're not seeing here the data, right? So, but our concern is going to be only to identify the confidence intervals. So the sample size. So it says here, level C confidence interval for a parameter is an interval computed of producing an interval containing the true value of the parameter. In this applet, we construct confidence interval for the mean of a normal population distribution. All right, each interval is based on a simple random sample of size n. The dot marks the sample mean, which is the center of the interval. All right, the lines on each side of the span confidence interval, the total numbers of the number hit, and the person hit are tail for you. All right. So it doesn't say anything as to what, I mean, it says only a normal population, but it doesn't say what, I mean, what is the mean of the population, all right? It says only that it is generating values from the population and it is computing the confidence intervals, but it doesn't say what kind of population. All right, I think it's not important. All right, so for example, let's say that by default, let's say the sample size equal to 20. Notice, or yeah, I can move this slider to 20. The confidence interval is 95%. And if I click once, I'm going to obtain one confidence interval. You see, only one confidence interval. So these are the values from the population, generated from the random. It should be 20. And if we compute a confidence interval for this, notice how this portion, this segmental line, it hits the green line. If it hits the green line, that means that the true value for the population mean has been covered by the confidence interval. So what about we do it for, I don't want to press reset. What about we do it for sample 25? In this case, we're going to obtain 25 confidence intervals. Yeah, before we obtain only one, now 25, notice. You see, 25 confidence intervals. Notice how each segmental line with the dot in the middle represents a confidence interval. Notice the ones in red, they do not hit the line in green. That means those values, they don't cover the true population mean. So when we construct that confidence interval, we hope that that value is going to cover the true population mean. But how many times? Well, that's going to depend on the level of confidence. In this case, it's supposed to be that 95% of these intervals would cover the true population mean. I know in this case it's not true because we have only the person hit the number of times in proportion that these intervals are covering the true population mean is only 88%, but this is because we have only 25 intervals. If we repeat this process in the long run many times, that number is going to be close to this number per person hit is going to be close to 25%. And actually, we increase the sample size as well. But well, let's start with the activity. Explore this concept by clicking on the green button sample 25. This will generate confidence interval for each of 25 independent replications of an experiment with n equal to 20. So I just did it here. Yeah. Now, increasing the level of confidence. What happened to the width of confidence intervals? Use the applet. Set confidence intervals to 95%, n equal to 20, and click sample. So we already did it. Now change the confidence level by moving the slider to 80%. So we're going to decrease the confidence level. So 80%. Yeah, the minimum we can have. And then sample 25. What happened to the width of the what happened to the width of the confidence intervals? The width for each interval has decreased. You see that? From 95% to 80%. So let me do it again. Reset. Confidence interval. Let's set it to 95 as before. The sample size to 20. And now I'm going to generate 25 confidence interval. Notice, these are the segmental lines, but if we do this, but now I change the confidence level to 80, and I generate 25, it seems like the width for the intervals has been reduced. You see that? So again, we can see this better with 1, and now change it to 95%. So the width of the intervals, no, it doesn't show here what's happening. What happened to the width of confidence intervals? Use the applet set confidence interval to 95% and equal to 20. Quick example. Now change the confidence level by moving light to 80%. This is supposed to be making the confidence interval to increase the confidence interval, but here it doesn't seem that this is happening, right? Well, no problem. When you reduce, yeah, I said it wrong at the beginning, but when you reduce the level of confidence, the length or the width for the interval is going to be bigger. Yeah, it's supposed to be bigger. That means that we have more probabilities to catch up the numbers. Yeah, but to catch the numbers. But anyway, since the interval is very big, maybe it's not, that information is not very relevant, right? I mean, how can be useful for you to know that, for example, that the mean is for example, for the mean height for students at UTEP, how is that relevant for you to know that the mean for the students is between 0 and 200 centimeters? I mean, of course, that should be the case for almost all the students, right? But that's why, but the interval is very big. We want to have a small interval and with a high level of confidence. But I think this is not reflected here. Anyway, so leave it like that, no problem. Now, step 2, increasing the sample size. What happened to the width of confidence intervals? Use the applet set confidence interval to 95%, n equal to 10. Now I'm going to reduce this to n equal to 10. All right. First, to make the comparison, 95%, I'm going to use it for 20, and I'm going to take one sample. There you have. Now I'm going to change the n equal to 10, and then one sample, and now change n equal to 100 by moving the slider to 100, and then sample. Notice, in this case, I think it's clear that the interval, the width for the interval has been has decreased. That okay? Has decreased. It's very small. Why? Because this means that we're going to have a more accurate interval, and that makes sense because we have the sample size is very big, so we have a lot of information from the sample. That's why this interval is going to be very precise. Well, more precise, I mean. Now, increasing the population standard deviation, what happens to the width of confidence? Use the following exercises as an illustration. All right, so we have to use this formula. First, we have to compute x bar minus t. X bar is 1 minus t with 2 asterisks times 0.5 divided by the square root of n. In this case, n is equal to 20. You will have to compute this formula with these values. The values, oh my God. The values I got here is for the lower value is 0.766, 6, comma. What about the upper value? I got 1.234. There you have. So use this formula and this formula, the lower bound and upper bound, with these values. I got this. Now repeat the process, but now do it for the same values, but change the s to 1. Before we use the s equal to 0.5, now we're using the s equal to 1. If you compute that, I got this 1.468 for the upper bound and 0.53 for the lower bound. So what happened to the interval? Notice when we increase the standard deviation, the interval becomes, is increased. The interval increased, and that makes sense because remember the standard deviation is a measure of variability, so we have more variability data. So the interval is not going to be more precise. And actually we can see this from the formula. Notice this formula, if this value of s is increasing, oh my God. I'm sorry. If this value, if this value of s is increasing, all of this number, t times s divided by square root of n, is going to be bigger. So we're going to be subtracting something bigger, and here we're going to be adding something bigger because we have a plus here. So the interval is going to increase. All right, label the width of the confidence interval as increasing or decreasing for each change. If we reduce the confidence level, the interval is supposed to be increasing. So here is going to be increase. Going from 10 to 100, decrease. And here, increase. Yeah, if you reduce the confidence level, you're going to have a wider interval. if you increase the sample, you're going to have more information, so you're going to have a better interval. So going from 95% to 80%, no, wait a minute. I'm sorry. I got confused, so let me do it again, the first part. Increasing the level of confidence. So we went from why it says here increasing? It's supposed to be decreasing from 95 to 80%. So I'm sorry, let me repeat this experiment, all right? Because I got confused. So reset, we start with 95 confidence level, the sample size is 100, sample 25, so we take one sample. There you have. But let's use it with 10 equal to 20. Now, if we increase, but why is it here increasing? If we are decreasing the level of confidence. I mean, I think it's a mistake. So if we decrease the level of confidence, the interval is going to be, if we increase the level of confidence, the interval is going to increase, the width for the interval. But if we decrease then the level of confidence, the width for the interval is going to decrease. Yeah. But why is it here increasing? And we are reducing this from 95 to 80%. I'm sorry for this. So here, sample size. Now I'm going to decrease this to 80. And sample. Yeah, should be smaller. You see that? To get convinced of this, notice, for example, what about if I use the maximum possible confidence level? So it doesn't keep the other one. So, well, I'm sorry. So you can see that if we are reducing the level of confidence, what's happened to the intervals? They are decreasing. You see that? If we increase the confidence level, the intervals are increasing. Yeah, I'm sorry, I got confused because it says increasing here, but we're going from 95 to 80%. So that's why but here we are not increasing, we are decreasing 95 to 80%. I'm sorry. So when you decrease the level of confidence, the interval, the width decrease. I'm sorry for that. And you can verify this. We decrease the level here in the left. We decrease the interval. The width of the interval decrease. If we increase the level, the width of the interval decreases. You see that? Increases, I mean. Decrease confidence level, the interval decreases. By increasing the confidence level, the interval is increasing. Yeah, I'm sorry. So from 95% to 85% decrease. So I'm assuming that we can observe the same here with this sample size. Yeah. So the rest is okay. All right. Yeah, I'm sorry for that. I got confused because this should be decreasing the level of confidence. Because it goes from 95 to 80%, so we are decreasing the level of confidence. All right. Now decide if each statement is true or false. Approximately 95% of the times we report a 95% confidence interval, we correctly capture the population mean in the confidence interval. This is true. Now the number 2, suppose the 95% confidence interval for a population mean is given. One interpretation we could assign to this interval that 95% of the replications of the experiment will yield a sample mean between 10 and 25. This is false. Yeah, I mean, a 95% confidence interval does not mean that if we obtain that interval, the true value, the mean, is going to be there with a 95% of probability. No. The 95% confidence interval means that if we construct 100 intervals or many intervals, 95% of the times we're going to be covering the true value. For example, go back to the left. I'm going to reset everything. I'm going to choose a sample size of 40, confidence interval 95, and notice I'm going to generate several samples, several intervals. First 25, there you have. You see? The ones in red indicate that they do not cover the sample mean, the true population mean. But if I increase this many times, notice the accumulated is 475. Eventually the percent hit is going to be 95%, the value of the confidence interval. So the first one is true, the second one is false. All right, I'm sorry for this little confusion that I had. Yeah, I was confused because of this, but well, if you have any question, please you can let me know. See you in the next video.